Howdy, folks. My name is Arul Verma, and this week we're going to be going over threads and messaging. So the goal for today is to talk about the thread creation and kind of review thread creation as a whole from last lecture. Then go over the motivation behind message passing, give us some examples of basic message passing, and then go over some advanced message passing examples. So this is an example that we talked about last lecture in which we talked about spawning a single thread. So let's go over some of the key concepts in spawning a thread. The first thing to note is using a thread crate, and we use the keyword thread : spawn to create our thread. And we use the double bar to essentially indicate what parameters we're passing, one of which is the execution of what the thread is going to do. So some of the core concepts of the thread is that the thread is its own independent programming function almost, and that runs independent of this main program that we have here. So our main thread does everything inside fn main, but our child thread does everything inside of the thread : spawn, and it goes all the way to its own completion. Threads run independently of each other. So our main thread is running at the same time that our child thread is running. The main thread's progression has no effect on the child thread's progression. So the main thread keeps on going to our match handle.join while this child thread is also progressing. And this actually has some interesting implications. If we spawn multiple threads in a row, if we have, say, this let handle equals thread spawn and we do it 10 times, and our child thread doesn't have a match statement and it just has this print at the end, the main thread will finish its completion before one of our child threads probably will. And what this can cause is a race condition where one of our child threads doesn't reach completion, it doesn't terminate ever. And the way compilers handle this is when the main thread ends, all of its child threads, irrespective of where they are immediately killed. So one of our child threads may not have had a chance to execute or do some computation, but it may be automatically killed because our main thread finishes. So the way we resolve this is through something called blocking. And the way blocking functions work is they essentially stop the progression of our main thread by making sure that our main thread cannot progress beyond a certain point until all of our child threads are finished. The way this is done in Rust is through a blocking function, which we'll go over in more detail a little bit later, or through joining threads. And the way you join threads is by using a join handle. A join handle is just a struct that gives you permission to join on a thread, and it blocks the program until the thread terminates. So thread.spawn allows us to create our thread and gives us our join handle for the thread. So in this case, handle being our thread join handle. And then the .join function is our blocking function that essentially blocks our main thread until all of our child threads are finished. In this case, our singular child thread finishes. And if the associated child thread panics, an error is returned. Otherwise, we get OK, which implies that our child thread has finished and is finished properly. So what happens if we want to spawn multiple threads? Well, we kind of just maintain a lot of the same concepts. We use a variable called handles, in this case a vector, to contain all of our individual join handles. And we spawn 10 times in a for loop. And each handle is pushed into our handles vector. Now, another thing to note is that we use the keyword move here. And we use I, which is declared outside of our thread, inside our thread. Inside our child thread, I should say, sorry. And this has some interesting observations associated with it. Because of how we have for I in 0.10 outside, the inner thread does not actually have access to any of this data. It doesn't know what I is. So we have to give this I to our child thread. We're using the keyword move. And move just tells the Rust compiler that any data that I'm using inside our thread that doesn't already exist or isn't already known, you should take from the outside. And we just move that data the same way with ownership. We transfer ownership from the main thread to the child thread, and then it's immediately dropped from scope once the child thread ends. From there, we do the same thing. We use a for loop to go over all of our handles, and then we join on each one of the handles. Now, this is an example output from the code I showed earlier, and you can see that on running it two different times, we get two different results. These results aren't identical. And the reason for that is because threads are run concurrently. They are run in parallel. And there's no control we have over which thread comes first and which thread comes second. We can see here that our threads are spawned from 0 to 10 in that order. And intuitively, we seem to think that we should be getting 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but we don't because the threads don't run in that order. The first thread may not always be thread 0. and the last thread will almost never be thread 10 or thread 9. And that's just the nature of how parallel execution works. Parallel execution runs at its own speed, and the difference between these threads are often micro or nanoseconds. So this is another example of us doing essentially the same thing with multiple threads in move. We have our data in thread data, or like that data equals string, and then we have our mute handles, which is our handles for each one of our threads. And we create our for loop and we create each one of our 10 threads. Now, here's an addition to what we were doing before, where we have let data clone equal data dot clone. Now, before when we used move with I, we didn't have to do any form of cloning. But here for data, we have to very explicitly use the keyword clone in order to use the data inside our thread. And the reason for that is because of inherently how different pieces of data work. Before with I was just a primitive type. It is a integer, a Boolean, or a character. And therefore, it has inherently a copy trait built in, as we talked about earlier. So the move keyword looks for any way to transfer the ownership of that data. And in this case, I can be copied. So it's very low effort for the compiler to just copy that data over and give it to the child thread to use, while also maintaining ownership in the main thread. But for data clone, we have to explicitly move ownership. And that's because string does not have that copy data type. So we have to transfer ownership of the data in full. And therefore, to pass that data over, we have to clone it. Otherwise, data would go out of scope. So if this was just to be, say, like use data in here instead of data clone, data would go out of scope after the first thread finishes executing. And any subsequent threads that try to run will run into an ownership issue because data will have been dropped from scope and data will no longer exist. Now, one thing I omitted to mention earlier, but I should probably flesh out a bit more, is how we're using join. So what join essentially does is it stops the main thread from executing until the children thread reach that point. And if we go back here, we see that join handle has an error or an OK. So in this case, what join is doing is for each one of our handles, it's waiting to see an OK until we can move on. So join stops the main thread from executing until an OK is received, and then we iterate forward one handle. And this allows us to get all of our results at the same time, or with like get all of the results before the main thread finishes executing, and ensures that we never kill a child thread, really. So the question is, why are we doing parallelism in problem solving? We have like the concept of parallel threading and parallel execution, but why is it important? Well, it's important because when you have a problem that you can split up into multiple repeatable parts, it's much more time efficient to do that same job at the same time rather than doing it multiple times individually. So instead of using a for loop, it's just more efficient to do parallel programming. Now, the reason that it's not used in most computing cases that you guys have worked with up to this point is because it's very expensive computationally. So it takes a lot of CPU power, a lot of GPU power, and a lot of memory. But usually, and especially with modern day computers can support that level of parallelism, especially at the level that we're going to be working with in this class. So it's just very time efficient and to do this type of computation at the same time in multiple repeatable parts. And the way we can do that is, let me move myself to the bottom of the screen, is we can create threads to solve each individual repeated problem at the same time, which is the parallel part of our parallel execution. And then we can join the results at the end together in the main thread. And this allows us to put all the pieces together and get a final output. So this is a visualization of what that really looks like. In our main thread, this major cylinder represents our main data, and each one of these three parts represents 1/3 of the data that we're splitting into our threads. We then move over our thread data individually. So we copy it over, we break it in three and clone, we move it over into each one of our threads, and we do some computation here, which gives us a result. Now we want to take this result and we want to return it to our main thread. And this is kind of how parallelism works as a whole, which we combine all of our individual thread results and we get our final result. Now, join doesn't really give us a chance to share data, right? We never really in share with join, we never really got this result to combine our process. We only got to do the main thread to thread. So the way we can combat that is we can share data in between threads. There's two primary ways that data is shared in between threads. The first is through something called shared memory, which is a concept that's far beyond the reaches of this course, and it's fairly complicated to set up. But there's a much more intuitive and easy way to share data in between threads, and that's through something called messaging between threads, or MPSC. MPSC stands for multiple producer, single consumer. In this case, the multiple producers being each one of the child threads, they're producing data, and the consumer being the main thread, which is receiving your data. So there are some pieces of data you can get using the function MPSC sender and MPSC receiver. Sorry, not function. These are classes that are the receiver, sender and receiver of your data, respectively. And you can create them using the MPSC channel function. And this opens a communication channel between threads. So you give all of your senders your worker threads. You give this sender to your worker threads, and you give your receiver to the main thread. And this kind of lets you cross message in between your threads. So this is an example of doing some sample messaging, very basic messaging in between the child thread and the main thread. So this is how we'd go about creating a sender and receiver. It's relatively standard practice in Rust to use TX for the sender and RX for the receiver. So I'll be calling them just TX and RX in the future. But do know that TX stands for the sender and RX for the receiver, and this is the class. An MPSC channel returns to us a tuple of sender and receiver. So to use MPSC, we have to use the standard sync MPSC library. And then we do function main, and we create our transaction and receiver, TX and RX respectively, and we spawn, and then we move our TX into our thread. And then we have let val equals string from high. This essentially is just creating the data we want to send. And then we send that data through to our sender, and then we do dot unwrap. And then our receiver has to receive it using RECV, which is just receive, dot unwrap. And then we can print that data here. So this would just print our high. So this is a more complicated version of the same concept where we're doing a transaction and receiver. And one thing this does do that our previous code doesn't is it demonstrates how to use multiple transactions for the same receiver, multiple TX for the same receiver. In this case, we have two different threads that we're spawning. Here we're spawning one in this thread spawn section, and we're spawning another one in this thread spawn section. And we want our main thread to receive for both of them. So the way we can do this is by using the same clone concept that we talked about earlier. So our sender one, that our original sender, TX, we clone and we make sender one, in this case, TX1. TX1 also points to RX as its receiver. So in our first thread, we can say tx1.send val.unwrap, and it'll still send the data to the same receiver that it should. And now our second thread can also send data to the same receiver. And after which, and we do our receiving in our main thread. We do for received in Rx, print got received. And one thing to note is because of the way this thread setup is made, we can tell exactly what the output is going to be because of this for loop and the sleep. We know we're always going to get hi, then more, then from, then messages, then the, then for, then thread, then you. It'll bounce back and forth between the threads to pick which one's going to return the data. So before when we were doing our data recipient from in our main thread, we used for received in Rx, then we just checked received, and that works, but there's a more fluent way of doing it in Rust, which is to use a while loop. And essentially all this does is it receives either an OK or an error when all threads are dropped from memory. And you can collect all of your data from your threads using all the messages from your threads using the following snippet, which is just while OK message at string rx.receive print got message. And an example of this is in the bottom left, and you'll see it again in a little bit, where essentially all we're doing is we have our TX, we create our channel, and we do the same thing where we create a thread index for 0 to 10, we clone, we spawn our threads where we just send a message, and at the end we have that same while loop that we have in the left, or in the right here, where we just essentially go through and we go one by one, we say, okay, we got our message. It's the same thing that's happening here with for received in Rx, where in this case, our receive is just going one by one in our Rx vector of messages received and printing them, while this is doing the same thing, but instead it's manually getting the value and it's unwrapping with OK message. Now, one thing to note is that previously when we were doing messages, we had to join at the end. Join was our blocker, which made sure that the main thread didn't progress any further. In this case, we don't have any join. So why isn't there any fear of the main thread just reaching completion and killing all the children threads that aren't finished yet? The answer for that is actually because of how RECV works, or receive. RECV, and in this case, I want to make it clear, this is also an implicit RECV call. So it may seem that like RECV is not being used, but it is. It is being called here implicitly. So received implicitly is a blocker. It is is its own blocker that waits for all of the threads to reach completion before continuing. And this means that like we don't have to use join. We can just use the rx.recv call, and this while loop will essentially block until all of our child threads are finished. And the great thing about this is that whenever you have a message from your child thread, you get OK from rx.recv, and you'll get a message from each one of your child threads. And when all of your threads are dropped from memory, when they all finish completing, you get an error. And that allows us to break out of the loop and keep on going because that means all of our threads have finished executing. So this is an example of this is the same code I had here, just kind of expanded a little so you can see a bit better. But this does have one bug in it that I didn't mention earlier. And we'll just go through and see if we can catch it. So we create our sender and receiver, respectively, with MPSC channel. We have our thread index 0 to 10. And now we clone our sender, and we move our sender into our for loop. So now we have tx.clone.send message.unwrap. And while OK message, rx.receive, print ln got message. Intuitively, this seems fine. At a first glance, this seems very correct. It does exactly what it's supposed to. We're cloning our transaction, we're passing it into our thread using move, and then we're sending a message. The reason this isn't good code and the reason why this doesn't work is because of what I said earlier. All of our senders have to be dropped from memory in order for progression to happen. And all of our senders aren't actually being dropped from memory here. TX also points to our receiver RX, as do all of the clones. All of the clones are being dropped from memory once the thread finishes. So 0 through 10 clones are, 0 through 9 clones are being dropped from memory, but the original TX is not being dropped from memory. It still exists. It's still pointing towards RX, and it hasn't sent a message yet. So this while loop will go on forever because it's going to keep on waiting for this TX to send a message, which it never will because we've never had it send a message. So the way we combat this is by adding this one line of code, drop TX. And this manually drops the TX from memory and makes sure that our RX or RECV receives an error at the end. So that's the way we combat this memory management issue of having the original sender be still in memory once we have our individual pieces done. So this is the same example of uh, kind of messaging, but done with more relevant examples and actual computation. So before it was always very, um, all of our examples are very like, how do we send a message? And just like, oh, this is like a cool message we can send. But this is very real computation that you will be using in MP3 once you start it. So let's just break it down. What's exactly happening here? So we have a chunk size of 10,000, and then we have the number of threads be 10. So our maximum amount of data is going to be 100,000. Sorry, I realize there's a typo here. Uh, and now we have our data. So we go from 0 to our max data, in which case 100,000, and we're going to collect it all in a vector of size of just unsized ints. And then we create our receiver in our transaction, or our sender, sorry, I should say. And then for I in our 10 threads, we're going to start our data at the chunk size. So in this case, for our first thread, it would be 0. And the end value would be our chunk size forward. So we're going to do exactly 10,000 values in each thread. And then we're going to get the data that we want to give to our thread, our owned subvector of our original vector. And we're going to get that amount of data using our start and end indices and create a new vector. And we're going to clone it. And then we can clone our transaction as well. We can see here, we spawn our thread and we move all of our data into our subvector. And then we take that data that we moved from our subvector that we moved over, and we're just going to create an iterator of it and map it and then sum it all. And this allows us to essentially just send messages equal to 10,000 of our data at one time over 100,000 data set. After all of our threads are done, we drop our sender from existence, our original sender, and then we just aggregate all of our data at the end using the while loop that we talked about earlier. And we can see here we have total plus equals value, which just sums up all of the values of the 10,000 given here. So this is sum of all 10,000 values, and this sums up the 10,000 chunks that we were given, or the 10,000 chunks we were given, basically. Sorry, I should clarify that. Each thread sums all 10,000 values that were inside of its vector chunk given to it. And in the end, our main thread receives 10 values, each of which represents data of the 10,000 that has been summed together. And this while loop just sums those 10 values together. So that's all for today's lecture. I hope you had a proper understanding of threading and messaging. If you do have any other further questions, we have office hours this weekend and we'll always be open for help on the Discord. And yeah, thank you so much for listening. I know it was a very hectic and very uh, deep and very difficult lecture. So thank you for sticking around.